In this video, we will be going over some applications that relate to the dot product and the cross product. And we're going to start with work. So as a reminder, when a force is acting on an object so that that object moves from one point to another, we say that the force has done work. And work is the dot product between the force that is being applied on the object and the displacement. So what that will involve is the magnitude of the force, the magnitude of the displacement, and cos of the angle between those two forces. So our first example, a woman pushes her baby stroller a distance of 1,500 meters by a force of 89 newtons applied at an angle of 35 degrees to the roadway. Calculate the work done. So I'm going to start off by drawing a diagram. This dot will represent the stroller, just for simplicity. The stroller moves a distance of 1,500 meters, and there is a force acting on the stroller. That force has a magnitude of 89 newtons, and it is a force that is being applied 35 degrees with the ground. Now, we know when we use our work formula, the angle has to be when the vectors are tail to tail. So I'm going to take that 89 Newton force and I'm going to shimmy it down a little bit. And because 35 degrees is opposite to the angle I need, that is also 35 degrees. And now we can calculate the work. So the magnitude of the force is 89 newtons. The magnitude of displacement is 1,500 meters, and it's important that the displacement is in meters, not other units, times cos of that contained angle, which is 35 degrees. Punch that into our calculators, and we get 109,356.8 joules. So therefore, 109,356.8 joules of work has been done. The next type of application we've already done is torque, and that involves the magnitude of the cross product. So we will need the magnitude of the torque arm, the magnitude of the force being applied to that torque arm, and the angle between those two vectors. Now, as a reminder, torque is just that turning effect. So a 20 Newton force is applied at the end of a wrench that is 40 centimeters in length. The force is applied clockwise at an angle of 60 degrees to the wrench. Calculate the magnitude of the torque and the direction. So I'm going to start with a diagram here. Let's say the bolt is here. This is the wrench. The wrench is 40 centimeters in length, and there is a force of 20 newtons applied at the end of the wrench, and it is at an angle of 60 degrees to that wrench. So here's my torque arm. This is going to be the force. There's the 60 degrees. There's the 20 newtons. And it is turning clockwise. So the fact that it's turning clockwise means that the bolt is being tightened. So the cross product will be into the material that is being tightened. If it were going counterclockwise, the bolt would be loosened, so that would be out of the page. Now, before I go on to do the torque formula, I am going to shimmy that 20 Newton force. So it's at the tail of the wrench. And now using a Z pattern, this is also 60 degrees, and there's the 20 newtons. So now, our torque is the magnitude of the torque arm. So that's the 40 centimeters, but it has to be in meters. So 0.4. The magnitude of the force, which is 20, and then sine of that contained angle. And if we punch that into our calculators, we get 6.9 joules. Therefore, the magnitude of the torque is 6.9 joules, and it's into the material. The next application we're going to look at is the area of a parallelogram. Now, the area of a parallelogram that is bound by two vectors, let's say u and v, can be found by taking the magnitude of the cross product of those two vectors. So let's start off by proving that. And I'm going to draw a parallelogram first. And it's bound by u and v, so I'll say that's vector u, that's vector v, and then there's the parallelogram. Now, we know normally the area of a parallelogram is just the base length times the height. So here's the height. Now, the base we already know. The base would just be the magnitude of vector u. But this height, and let's say we have this contained angle between the two vectors, well, the height is opposite to theta, and vector v is the hypotenuse. So we would be using sine theta equals the height divided by the magnitude of v. And if we just cross multiply, we end up with our height being the magnitude of v times sine theta. So if we put those two things together, the area of the parallelogram is the base, which is the magnitude of u, times the height, which is the magnitude of v, times sine theta. And what does that remind you of? That is the magnitude of the cross product of those two vectors. So if I had the contained angle, I can just use the two magnitudes and sine of that angle. But if I'm given two algebraic vectors that represent the vectors that create the parallelogram, then I can just find the cross product and then take the magnitude. Now, if we know that the magnitude of the cross product is the area of the parallelogram, then the area of a triangle, which is just a parallelogram cut in half, would just be half of the magnitude of the cross product. So let's give that a try. The vectors A equals 362 and B equals 214 define a parallelogram. Determine the area of the parallelogram. Well, the area is going to be the magnitude of A cross B. So I'm going to find that cross product. So I'm going to start with vector A, and I'm going to start from the middle component, 6, 2, 3, 6. Then I'm going to write vector B starting from the middle component. And now I have 24 minus 2. I have 4 minus 12. I have 3 minus 12. And my cross product equals 22, negative 8, and negative 9. And now I just need to find that magnitude. So the square root of 22 squared plus negative 8 squared plus negative 9 squared. And if I'm keeping it in its exact form, that'll be the square root of 629 units squared. And that's the area. Now determine the angle formed between vectors A and B using two different methods. Well, when are the two times that I've seen theta? I've seen it in the dot product and I've seen it in the cross product. So we know that the magnitude of the cross product is equal to the magnitude of the individual vectors times sine theta. So sine theta would equal the magnitude of the cross product divided by the individual magnitudes. Well, we already did the cross product magnitude. It was 629. And now the individual magnitudes will be, for A, 3 squared plus 6 squared plus 2 squared, and for B, 2 squared plus 1 squared plus 4 squared. So what do we get? sine theta equals the square root of 629 over the square root of 49, which is just 7, and then the square root of 21. And then we can take the sine inverse of that. I'm not even going to worry about rationalizing the denominator because I need to take a sine inverse anyway. And I get 51 degrees. And that's using my cross product. But I can also use the dot product to find my angle because I know the following is true about the dot product. Multiply the magnitudes by cos of the angle, which means cos theta is the dot product divided by the magnitudes. And we already found the magnitudes. The magnitude of A is 7, the magnitude of B is 21, and now just the dot product between A and B. So multiply the x components, 3 times 2 is 6. Multiply the y components, 6 times 1 is 6. And the z components, 2 times 4 is 8. So cos theta equals 20 over 7 root 21. And if we take a cos inverse, we do in fact get the exact same 51 degrees. So 2 different ways to calculate our angle. In this scenario, I would have preferred using the cross product since we had already calculated the area of the parallelogram. Otherwise, I think the dot product might be quicker. So that's your area of a parallelogram. So we are doing base times height, but we're using the cross product and its magnitude to do that. Next, we have some applications that require a triple scalar product. Now, what's a triple scalar product? It is when you take the cross product of 2 vectors first, and then take the dot product between another vector and that cross product. Now, the reason I mentioned that you have to do a cross product first is because if you do A dot B first, then you end up with a scalar quantity, and you can't do the cross product between a scalar and a vector. So it is important that the cross product is done first. Now, one application of the triple scalar product is the volume of a parallelepiped, and that is a 3-dimensional shape that is created by 6 parallelograms. So, what is the volume? The volume is going to require 3 vectors, and these are the 3 vectors that define your parallelepiped, and that would be vector u and v on the base, and then this diagonal vector w. And the volume is going to be the absolute value of that triple scalar product. Why is that the case? Well, the volume of the shape itself is going to be the area of the base times the height. That's the area or the volume of any prism-like shape. So the base area we already saw from above is the magnitude of the cross product. But what about the height? If you look at the height, you can create a little right triangle here. And the height is adjacent to theta, and the magnitude of w is the hypotenuse. So cos theta equals the height divided by the magnitude of w, which means the height would be the magnitude of w times cos theta. Here it is. So there's the base area, and the w cos theta is the height. But what does this look like? This looks like the dot product, and it's the dot product between the first thing that you're taking the magnitude of, which is u cross v, and the second vector that you're taking the magnitude of. So u cross v dot vector w. So let's give that a try for this example. The volume of the parallelepiped defined by vectors a, b, and c. Now, the order that you do your triple product doesn't matter. And what I mean by that is if you do ABC, BAC, that doesn't matter. But of course, doing your cross product first is a must. So I'm going to say my volume is equal to the absolute value of A dot B cross C. So I'm going to do my cross product on the side. So I'll start with vector B, 6, 9, negative 4, 6, and then vector C, 3, negative 10, 3, 3. So vector A dot, and now here's my cross product, negative 60 minus 27, so negative 87, 27 minus 40, it's negative 13, negative 12 minus 18, negative 30. Now let's take the dot product, 6 times negative 87, negative 522, 3 times negative 13, negative 2 times negative 30. Let's add these up and we get 501, negative 501, which would be 501 units cubed. And now we can move on to our final application of that triple scalar product. And that is testing if three vectors are coplanar. So if three vectors exist within the same plane. And what we're going to test for is we're going to take the cross product of two of the vectors and then the dot product between the third vector and that cross product. And if you end up with 0, that means that your three vectors are coplanar. Now, why does that make sense? When you take the cross product of u and v, you're going to get a vector that is perpendicular to u and v. If all three of these vectors are within the same plane, they should all be perpendicular to that same vector that you get with the cross product. So if that's true, then the dot product between w and that perpendicular vector should be 0 if w is also within the same plane as u and v. If it's not, then the dot product will not be 0 because that vector that's supposed to be perpendicular to the third vector actually isn't. And again, the reason we're looking at 0 is because the dot product of two perpendicular vectors is 0. So let's test it out. Show that the vectors 1, 0, 1, 1, 1, 0, and 0, 0, 1 are not coplanar. And what do these three vectors span? Okay, so I'm just going to say this is vector A, this is vector B, this is vector C. I'm just going to take the cross product of the first two. So I'm just going to go below here. 0, 1, 1, 0, 1, 0, 1, 1. Now that's 0 minus 1, it's negative 1, 1 minus 0, and 1 minus 0 again. So that cross product, we're going to take the dot product between that and vector C. So that's going to be negative 1, 1, 1, dot 0, 0, 1. And we'll get 0 plus 0 plus 1, which is 1. The fact that we got 1 and not 0 means that these are not coplanar. If they had been coplanar, we would have gotten 0. So if they're not coplanar, that means these three vectors actually span R3. And that's it for our applications of dot and cross product. So once again, we have work that is applying dot product. We have torque that applies the cross product. We have the volume of a parallelogram and a triangle that involves the cross product. And then for our triple scalar product, we have the volume of a parallelepiped and checking to see if three vectors are coplanar. And this is actually a lot quicker to test if they're coplanar instead of trying to create a linear combination and seeing if it works. Because in this case, if I try to create a linear combination of one vector with the other two, I wouldn't have been able to do it because these don't belong within the same plane. But this is a lot quicker than testing out that linear combination.